Welcome to Adaptive Lanczos. My name is Timothy Lanczos, and this is the Neo Kino Graphics channel. This talk is going to be a talk about doing it the wrong way, but better. When you're giving the finger to the viewer in the form of maximizing temporal flicker in the quest for maximum eye-bleeding sharpness, i.e. trying to amplify a Nyquist, this will be a guide on an adaptive sharpening kernel that you can use that functions like CAS, but provides something that works in a custom MSA resolve, or for instance in the custom octahedral to cylindrical projection, which is what I used it for. Before we begin, definitely do the filtering in linear. If you do it in perceptual, you're doing it wrong. The aim here is that if one is going to amplify Nyquist, at least try for something energy conserving so that the flicker from a distance disappears. My prior use case was a cylindrical projection. I was running into an octahedron projecting 360 degrees. Initially I was trying 240p, which you can see from the screenshot on the left, and later I moved over to 480i. Of course, my intended usage case was for 15 kHz PVMs. So I would render at 480p at 60 Hz, and then I would use a box that did alternating even and odd line strip for even and odd frames to get to 480i at 60 Hz. And then I also used the PVM 16:9 aspect button so that I improved the vertical resolution compared to if I just letterboxed it. Now you'll note this is extremely small resolution compared to 4K, but I wanted to see how detailed it could be with full cheating, i.e. what if I just maximized amplification at Nyquist as much as you could possibly do. So now we're going to dive into what the filter kernel that I was using for this experiment. This is the general form of a Gaussian and Lanczos approximation, and I used this in the form of a radial kernel. So the actual radius would have been Jinx 2.0 times 1.21966999. And I would map that to 1.0. And this kernel's remapped zero crossing is at 0.5. And the reason I use a negative 1-to-1 kernel in the scaling is so that I can use saturate. You'll notice that in this, the p equals integers are the fast forms that don't require an expensive power. So you can see the green curve is a bell-shaped curve similar to a Gaussian. And the red one is the one with negative lobes, similar to the Lanczos. The negative lobe is adjustable. You have some control over the amount of the negative lobe. However, when you blend between the two kernels, the zero crossing moves. One of the nice aspects of this approximation is that the two kernels you're blending between are, in this case, represented by a, which is the function, and then b, which is just a squared. So the math is very simple to calculate. In this case, we'd be using n for the blend ratio, and when n is equal to k, you can see k is computed from p, which is the power, which controls the strength of the negative lobe. When m equals k, you get zero crossing at 0.5. So as m approaches 0, you get something that is more Gaussian-like, which has less negative lobe. When you venture into a negative n, you're pushing into more of a DOF-like kernel or depth of field style kernel. You're getting lobes that ring around 0. I was using this property to have the ends of the screen go out of focus. Note that the values are going to be above 1, so you'd always want to renormalize this kernel. Now we're going to talk about contrast adaptive sharpening, in linear of course, with respect to this kernel. So first you need to do an extra hard or soft min and max kernel. Hard would be like only mins, and soft would be like a blend of two different mins, preferably the soft one. With the min and max kernel, now you have local contrast, i.e. take the max minus the min, as well as the distances to the signal bounds, which is where overflow would happen. So now one can compute the M blend ratio such that the sharpening is modulated, similar to how CAS works. And this can be done based on an amount that both won't go out of bounds and won't sharpen too much given the local contrast. And this is how you do good linear space filtering, because traditional linear space filtering would typically have dark outlines, which are very visible. So my monochrome project, I'm showing you the source code on the right-hand side. I did not need to limit the ringing, and that is because I was doing some super sampling and the ringing was not visible. However, if you're not doing super sampling and you want to limit the ringing perceptually, what you would do is you would change that m.y term to m.y times ringing. And note, you really only have to use the dark side to limit ringing because that is the one that is highly perceptual. The light side is not. The light side is mostly used to make sure you're not exceeding signal bounds so that you're losing energy. Now we're looking at this approximation versus the real Lanczos 2. You notice that P4 and P equals 5, those cases basically wrap the actual Lanczos 2 curve. There are some alternatives you can do with the lerping between two functions. You can use different P terms for the two functions that you're lerping between. So one option is use P equals 16, which is the Q curve in this case. Use that one for the Gaussian one, or the one that's almost like a Gaussian, and use something crazy for the negative lobe, such as P equals 2, for the one that is the maximum that you can do for the sharpening. However, you notice that as you blend between these two kernels, you get something that is far away from the real Lanczos 2. So in this case, the dashed black line is the real curve, the green one is the blend, the red one is the Gaussian-like one with almost no lobe, and the orange one is the one with the crazy lobe. If we want something that blends closer to Lanczos 2, we can adjust one of the curves to the P equals 4. However, this tends to flat spot the kernel at the top. So we got two examples at the bottom. The one on the left is showing the blend closer to the Lanczos 2, and the one on the right is showing one of the extremes of the blend with the most amount of negative lobe. You'll notice that using the P equals 16 curve, this tries to keep sharpness by pushing closer to a zero ring impulse. So sharpness in this case comes at a cost of increased aliasing instead of ringing. So let's leave with some closing notes. These kernel examples are for filtering without feedback. If you're filtering with feedback, for instance in a TAA, you would want to do something completely different in the design due to the temporal effects. And also, I have to apologize in advance for swapping the CZ for the ZC. I am dyslexic.